Thank you, Chiara, and I'm Luisa Puigmonet, and I will present the work we did last year with the Estrella Almeida and Antonio Turiel from the Institute of Marine Science in Barcelona. And this was part of my bachelor thesis in mathematics. The work's title is called "On the Relationship Between Singularity Exponents and Finite Size Lyapunov Exponents in Remote Sense Images of the Ocean." And what I will try to do is to explain two different mathematical concepts that describe the state of the ocean, and within that, try to see if how we can detect and position transport barriers. Our goal is to see if they can be detected by any remote sense data and not only by the velocities. The concept of singularity exponents, I wanted to point out that was already introduced by others, but in particular by Cristina Gonzalez in one of her talks in February on the evaluation and intercomparison of GHRSST permitted products in global scale. Well, the structure of the talk, first I will try to give the mathematical definition and the intuitive idea of both exponents, and then I will try to show a preliminary comparison between them that we did, and propose or further ideas on how we could see how they are correlated. The Lyapunov exponents are a measure of dispersion and tell us the exponential separation between two particles that are initially close to each other, and to see this exponential rate of separation. They come from a Lagrangian analysis because you use the trajectories of the particles to compute those exponents, and therefore you need to know the velocity field. What I will try to explain in further later, it's how the Lagrangian Coherent Structures are the mathematical definition of what we call transport barriers on the sea, and those transport barriers are important to detect for various applications in marine and maritime sciences. Then these Lagrangian Coherent Structures can be understood or can be defined as the local maxima of the Lyapunov exponents. So therefore, we could be detecting with the Lyapunov exponents what are called the transport barriers. But we need the velocity field, and to avoid that, the approach I will explain is an approach based on the singularity exponents. And the singularity exponents, what they are showing us is the irregularity or the grade of differentiability of the signal in the ocean. And they reveal what's called the multifractal structure of the flow. We need to remember that the ocean is a turbulent flow, and therefore we have the Kolmogorov theory telling us about the energy dissipation, and that generates a multifractal structure on the flow. And we will see this structure, like the singularity exponents reveal us this structure. And what I will try to do is try to compare the multifractal structure revealed by the singularity analysis with the Lagrangian coherent structure that in the same time we know that it's related with the transport barriers. I want to note or to recall that I'm not trying to show equivalence between those exponents for now. I'm just trying to see if up to which extent they are correlated, because the singularity exponents are dimensionless and the Lyapunov exponents are of units inverse time. So they cannot be equivalent identities. Let's talk a bit about how we define a Lagrangian coherent structure mathematically, and why is it related to the transport barriers. Well, we can consider the function f, which be the function of the flow of the trajectory of a particle, and within that we can define the concept of material line. A material line is just a smooth curve of particles affected by the flow and creating a later image of themselves. Then we can divide the material lines into types. The attractive material lines, which would come from if you give a perturbation on the line, this perturbation would converge to the line, or the repelling material line that if you give a perturbation, it would diverge. And then we define the Lagrangian coherent structures as material lines retaining their stability for longest times, either in the attractive or repelling sense. And therefore, since we understand the Lagrangian coherent structures as lines of particles, as lines of particles where the particles are either super attracted or repelled, any particle could be crossing the line, and here it comes the concept of transport barrier. Mathematically, to detect the Lagrangian coherent structures, what we do is to consider the function epsilon, which is the function of the maximal growth over the most repelling direction. So for every point x, epsilon, the function epsilon, would be detecting the most repelling direction and keeping the eigenvalue. The eigenvalue of the Hessian matrix is how it is computed, of the Hessian matrix of the function. Then we define the concept of the function lambda, which would be what we call after the Lyapunov exponent. And the Lyapunov exponent lambda is computed using, again, the maximum of the eigenvalue of the Hessian matrix, and it's relating with the function epsilon just by the integration in time. So it's actually the exponent that we see here on the rate of separation of two particles. Here I show the type of map we were using in our study. The source is Aviso Plus, and it's a product where the exponents are already computed. They are computed concretely backwards in time, and what we are seeing is the most negative exponents showing us the transport barriers. I want to note that what we used, it's not the Lyapunov exponents, but the finite size Lyapunov exponents. We can see in the most energetic regions of the ocean that we have the most negative exponents, and therefore the transport barriers, the most marked transport barriers. This would be, for example, where we have the Gulf Stream or the Angola's current. Now I will briefly introduce the concept of finite size Lyapunov exponent, because the thing is that since to compute Lyapunov exponents we need the velocity field, but the velocity field comes from remote sense, and therefore it's a discrete concept in space and time. What it's usually done is to use the finite time Lyapunov exponents, but those exponents are hard to compute in terms of memory and time consuming, because to compute them, what you would need to do is to integrate over different, you fix the time and you find the rate of separation. But to find the rate of separation or the maximum eigenvalue, you need to diagonalize matrices for a very long integration times, and that takes a lot of time. To be more efficient, what is usually done is to compute the finite size Lyapunov exponents that come from the exactly same definition or formula, but just that you fix in a space and you see the time that takes for each direction to reach this space of separation. Now that I have talked a bit about the Lyapunov exponents and clarified that we're using finite size Lyapunov exponents, I will go back to the singularity analysis. Well, as I said, the singularity analysis is trying to reveal us the multifractal structure. But what's this structure? Well, to define that, I will define the concept of singularity exponent. And we define the singularity exponent, the most basic definition is by the use of the pseudo-Taylor expansion of the signal. And we have it here in the formula in the screen. And the exponent is defined as a function h of x. Therefore, the exponent is telling us the degree of differentiability of the function. So if the exponent is in between 0 and 1, we would have that the signal in that point is continuous but not differentiable. And if we find exponents greater than 1, we have that the function is differentiable already. This is important because it's the concept that relates us with the fact that the exponent is telling us the degree of irregularity of the signal. Irregularity in the sense of if the signal is continuous or differentiable. we define then the fractal components as the set of points sharing the same exponent. And these fractal components can have different dimensions. We will see it in the next slides. But first, I want to talk about how we compute the singularity exponents, because it's important in the terms of when we are interpreting our results. So the singularity exponents are a sensitive quantity to compute, and therefore it's almost mandatory to apply wavelet transformations on the signal before computing them. So we would be always computing the singularity exponent over a wavelet transformation, but this wavelet transformation leaves the exponent invariant. But then another improvement to compute the singularity exponents and get greater quality is to compute the exponents over the gradient of the function, and that is affecting that's affecting the singularity exponent by decaying by 1 unit, because we are computing over the gradient, and of course we lose a degree of differentiability. And that's important because if I show you the singularity exponents we get, the interval where we have them is from -0.5 to 0.5. And that would be, since they are computed, since we computed with an algorithm that does a wavelet transformation and it's over the gradient, that would be that the negative exponents are areas corresponding to areas where the function is differentiable, is continuous but not differentiable, and the positive exponents is areas where the function is already differentiable and therefore less irregular. Well, I want to mention that what we did here is compute the singularity exponents from a daily map of SST taken from Copernicus, and I want also to recall that in the most energetic areas we have the most negative exponents corresponding to fractal dimensions of 1, because we have curvilinear shapes, and in the most less energetic areas we have the positive exponents and the less irregular areas, and then the fractal dimension is 2 because we have unclear shapes. Now I will go on showing you how we tried to compare both exponents, and our goal was to try to explain the finite size Lyapunov exponents in terms of the singularity exponents. That's why we represent always the finite size Lyapunov exponents in function of the singularity exponents. In the left, we see a density plot of all the pixels, of all the values of the pixels in the map. This is always, in this work, we always worked with daily data. So only comparing a map from one day to the other, and we work globally and then regionally. So what we see here is the density plot normalized by the total number of pixels falling in a value of singularity exponent. And we see that for the positive singularity exponents corresponding to the areas where we have fractal dimension 2, there's no clear relationship. But in the negative exponent, for the negative singularity exponents, we see that they might be a relationship. And to picture this relationship, we have done a simple linear regression over the mean value of the finite size Lyapunov exponents. This first functional relation approach is really simple. And since we are considering the mean value of the finite size Lyapunov exponents, the relationship is not invertible. Also, we note that we are overestimating the value of the finite size Lyapunov exponents, because in the real map we get exponents up to -0.4, and here we are staying up to -0.15 in this case, and this is a restriction on our functional relation. Also, well, I note that here for the positive singularity exponents where we didn't have a clear relation, we just estimated by a constant to then be able to reconstruct with our functional relationship that, I repeat, is super preliminary, the finite size Lyapunov exponents via the singularity exponents. And here we can see the map of the reconstruction and the map of the absolute error. I want to note that where we have the highest absolute error corresponds to the regions with highest energy. And that's because we are overestimating the value, as I said before. We are overestimating the value of the finite size Lyapunov exponents. But here, analyzing the accuracy we got to explain the 70% of the pixels with an accuracy of 0.05, which is quite high. Now, to understand where our errors might come from, what we did is to also compute the singularity exponents from an image of the ADT. The altimetry is also the altimetry and the SST should be giving us the same fractal structure, or should be representing the same fractal structure, because they are coming from the same vector flow. In big terms, in general terms, we see that they are definitely showing similar structures, but if we go closely, the singularity exponents from the ADT are more rough and thicker, and they not always match the singularity exponents of the SST. That's one of the reasons. It's highly because of the retrieval processes of the remote sense data that gives us the altimetry and the SST, and give us to think that our errors might come in part from the original data we are using to compute the singularity exponents. Now here I want to show a bit that concept with the same plot I was already showing. And we see that if we compare globally, this would be from a global comparison and daily, from the altimetry exponents with the temperature exponents, we see that for the parts, the areas with fractal dimension over 1 or positive singularity exponents, we don't have a clear relation, but we only have that they are matching for the negative exponents. Then if we see how the finite size Lyapunov exponents are explained by the singularity exponents from altimetry, we see that we are not overestimating as much as with the SST, and that we are getting a similar shape as the one we get before. So at least we get what it would be a similar relationship. Now I wanted to go closer to regions. First, the Angulus current. We see that seeing the normalized density plots, we see that we are missing a lot of data compared to the global, and that makes us think that, of course, to go deeper on this analysis, we should use integrated maps on time and just more data, because this is not enough. But it reveals us, comparing the exponents, it reveals us that the relationship is better. And it's better most likely because in this area, we have most of the exponents are of fractal dimension 1 and really negative. And then the relationship can be better compared. Then if we go to the South America, where we have the Brazil-Malvinas confluence zone, we also get a better relationship that with the global. But in this case, the ADT is failing to explain us the Lyapunov exponents. And that may be because in this part, we are getting a really rough signal of singularity exponents of ADT. Well, finally, I wanted to summarize a bit all the ideas and all the further work it can be done, and all the limitations on this comparison, because I think one thing that needs to be considered it's if the equivalence is also holding in areas with fractal dimension 2, or we can just have or consider or aim to find a correspondence in areas with fractal dimension 1. Also, if we should be considering both attractive and repulsive Lagrangian Coherent structures, because with the backwards in time exponents, we are just considering the attractive Lagrangian Coherent structures. Then, to improve the comparison, I think we should first use extended temporal series of satellite images, and maybe combine different advective variables like SST, ADT, or salinity, or chlorophyll signal to produce the singularity exponents. Then, of course, try to fit a better or finer functional relation. Maybe also it could be done a closely geometrical study on the shapes we are getting on the maps. And all these things would give us temporal stability on the relationship to assess if the relationship is stable temporally, and to assess where is it holding, and if we can aim for a relationship in which areas we can aim for a relationship, how big they have to be, and also if it's a seasonal relationship, if it can be a yearly relationship, or which type of relationship we could get. Well, that's all. Here we can see the references.